A silent tension is building beneath Earth's crust, and the signs may be coming from over 90 million miles away. Scientists tracking solar activity have identified a troubling pattern. A colossal coronal hole on the surface of the Sun, now rotating toward Earth, may be influencing the delicate balance of tectonic pressure that governs the timing of large earthquakes. After 8 months of abnormal solar behavior, experts believe we may be entering a critical seismic window. Earth is currently experiencing an unusually long pause between major earthquakes. It has been more than 3.5 years since a magnitude 8 or higher quake shook the planet, a stark contrast to the usual rhythm of one such event per year. Rather than a cause for comfort, this seismic stillness is increasingly viewed as a warning. In geophysics, a prolonged lack of major earthquakes often signals accumulating strain along fault lines, potentially setting the stage for a massive release of energy. Amidst this rising concern, attention has shifted toward an unconventional but increasingly studied driver of seismic activity, the Sun. A vast and persistent coronal hole, now completing its 8th full rotation since first appearing in October 2024, has been growing in both size and influence. Now spanning roughly 1/4 of the Sun's visible face and measuring nearly 8 times wider than Earth, this solar anomaly is aligned to directly face our planet. The upcoming week presents a particularly sensitive window. Due to the hole's immense breadth, stretching from the Sun's equator toward its southern pole, Earth will remain in its crosshairs for nearly 7 days. This prolonged exposure to intense solar wind streams could dramatically elevate the likelihood of seismic triggering, especially in regions already strained by tectonic stress. The potential connection between such solar disturbances and earthquakes is no longer speculative. Historical data reveal that the catastrophic 9.1 magnitude quake off the coast of Japan in March 2011, which led to the Fukushima nuclear disaster, coincided with the appearance of a similarly structured coronal hole facing Earth. The parallels are striking. Both events occurred during periods of solar maximum. Both featured anomalously large coronal holes, and both displayed similar solar latitudes. More recently, on March 28, 2025, a powerful magnitude 7.7 earthquake struck Myanmar during the 7th rotation of the very same coronal hole currently being monitored. That quake triggered a cascading global response, with 3 additional magnitude 6+ events erupting across various fault lines within mere hours. Seismologists refer to this as a global seismic burst, a pattern of distributed, simultaneous quake activity that hints at a planetary-scale mechanism linking solar and tectonic dynamics. What gives these coronal holes their potential to disrupt Earth's seismic balance lies in their unique magnetic structure. Unlike other regions of the Sun's surface, these holes feature open magnetic field lines that channel solar plasma outward at exceptionally high speeds. These streams, known as high-velocity solar wind, can interact with Earth's magnetosphere and, some researchers argue, subtly modulate the stress distribution within the planet's crust. Recent observations have highlighted a unique and potentially consequential aspect of certain solar phenomena: fast-moving solar wind streams characterized by extremely high velocities, often surpassing 650 kilometers per second, and unusually low plasma densities. When these intense streams collide with Earth's magnetic field, they set off a cascade of interactions, not just in the magnetosphere and ionosphere, but possibly within the lithosphere as well. An intriguing and recurring pattern has emerged from seismic records. Many major earthquakes have occurred during periods when the solar wind's plasma density fell dramatically, sometimes dipping below 0.1 particles per cubic centimetre, a stark contrast to the more typical 5 to 10 particles per cubic centimetre. Plasma physicists interpret this disparity as an osmotic gradient, a kind of pressure imbalance that may cause charged particles from Earth's inner layers to migrate toward the surface and out into space. If such a plasma flow happens near fault lines, it may act like a molecular lubricant, weakening the friction that holds tectonic plates in place and possibly triggering a sudden release of stress, a seismic event. Support for a solar seismic connection has grown steadily with each new dataset. A comprehensive review of the most powerful earthquakes recorded in 2024 revealed that nearly all of them coincided with the presence of Earth-facing coronal holes, massive gaps in the Sun's outer atmosphere that are known to emit high-speed solar wind. The sole outlier occurred during a G4- geomagnetic storm, itself a significant solar-driven disturbance with the power to disrupt Earth's electromagnetic environment from the upper atmosphere down to the crust. What makes the present conditions especially alarming is the simultaneous occurrence of both triggers. A recent G4-class geomagnetic storm and the steady approach of a large, persistent coronal hole toward direct Earth alignment. The geomagnetic storm may have already sensitized Earth's geophysical systems, making them more susceptible to external stimuli from incoming solar wind beginning around April 22nd. Looking at historical trends, regions most vulnerable to high-magnitude earthquakes, specifically those exceeding magnitude 8.5, are predominantly found along the Pacific Ring of Fire. This volatile zone, where oceanic plates are forced beneath continental plates, includes seismic hotspots such as Japan, Alaska, the western coast of South America, and the Cascadia subduction zone in the northwestern United States. Each of these areas contains deeply stressed fault systems that could rupture under the right conditions. The convergence of several geophysical risk factors, Earth's long-overdue status for a major quake, the nearing Earth-facing position of a coronal hole, recent geomagnetic disruptions and heightened solar activity during the current solar maximum suggest a period of elevated seismic risk in the immediate future. Statistical links between solar events and seismic activity have become increasingly difficult to ignore. However, it's the emerging understanding of the mechanisms behind this correlation that reveals the deeper significance. The solar wind emitted from coronal holes differs markedly from ordinary space weather. It brings not just speed but scarcity, a near-vacuum state in terms of plasma density. This sets up an extreme osmotic gradient between space and Earth's interior, encouraging an outflow of energy that may subtly undermine the stability of Earth's crust. The traditional image of Earth as a passive solid sphere is being steadily challenged by new discoveries suggesting far more complex dynamics within its core. One such idea gaining traction among researchers is the Georeactor Hypothesis, the notion that a natural nuclear fission reactor exists at the planet's center. This concept, once considered fringe, finds support in the physics of planetary formation. Dense elements like uranium would have been naturally drawn toward the core during Earth's early development and, under the right conditions, could sustain a long-term nuclear chain reaction. If this hidden reactor exists, its implications are vast, especially for understanding seismic activity. Nuclear fission doesn't just release heat, it generates a variety of charged particles and lighter elements, effectively forming a type of plasma deep within the Earth. This may help explain the continuous emission of helium, particularly helium-3, from subterranean sources. Such emissions are puzzling under conventional models, as helium, being both inert and light, should have long since escaped into space. But if it's being actively produced through ongoing nuclear reactions, the mystery becomes clearer. The intersection of this internal plasma generation with Earth's geologic systems presents a compelling scenario. When solar conditions create an outward gradient, effectively pulling plasma toward the surface, what happens when this flow meets zones of tectonic stress? The answer may lie in the ability of ionized particles to interfere with the chemical and physical bonds within rocks. As this plasma moves across a fault line, it can disrupt molecular structures, weakening the electromagnetic forces that bind crystal lattices together. In practical terms, it's akin to reducing friction between locked geological plates, allowing built-up stress to release suddenly and violently, in other words, triggering an earthquake. This hypothesis offers a new lens through which to interpret earthquake lights, the mysterious, luminous phenomena reported during powerful seismic events. Rather than anomalies, they could represent visible manifestations of plasma discharges breaching the crust, brief windows into Earth's hidden energy systems. The electromagnetic nature of seismicity doesn't end with visible light. Seismologists have recorded unusual electromagnetic signatures, particularly in the radio frequency spectrum preceding major earthquakes. These signals often appear days or even weeks before the ground moves, defying explanation under purely mechanical fault models. Global atmospheric resonances, such as the Schumann resonances generated by lightning, also exhibit measurable anomalies before significant earthquakes, reinforcing the idea of an electromagnetic component to tectonic behavior. Satellites have further advanced this view, detecting ionospheric disturbances in the hours and days before large quakes. During the 2011 Tohoku earthquake in Japan, measurable shifts in the ionosphere's electron content were recorded, essentially a massive electromagnetic pulse emanating from beneath the crust. Similar patterns have emerged in data from other catastrophic events, hinting at a deep and previously overlooked connection between Earth's inner energy and its atmospheric boundaries. All of these effects become markedly more intense during periods of heightened solar activity. The current solar maximum, characterized by a surge in sunspot formation, floods Earth's ionosphere with vastly more X-ray energy, up to a 1,000-fold increase compared to solar minimum. This influx supercharges the global electric circuit and may elevate plasma levels within the lithosphere itself. In such a charged environment, Earth becomes increasingly sensitive to external solar triggers, potentially setting the stage for larger and more frequent seismic events. The current situation presents a deeply unsettling convergence of risk factors. A persistent coronal hole on the Sun, first observed in October 2024, has now survived 8 full solar rotations, expanding with each return. During its 7th rotation, it coincided with the powerful March 2025 earthquake in Myanmar and a broader surge in global seismic activity. Now, larger than ever in its 8th cycle, this coronal hole is poised to usher in a prolonged phase of unusual solar wind behavior, projected to begin around April 22nd. This cyclical pattern of coronal hole reappearances and their cumulative effects is eerily reminiscent of the conditions preceding the catastrophic 2011 earthquake in Japan. In that case, successive solar windbursts linked to coronal holes struck Earth in a rhythmic sequence. Data showed not only spikes in solar wind velocity but also precipitous drops in plasma density, signatures that emerged just before the magnitude 9.1 disaster struck. Such patterns challenge conventional thinking. The growing body of evidence pointing to an electromagnetic link between space weather and seismicity marks a potential paradigm shift in geophysics, whereas classical seismology centers on the gradual build-up and sudden release of mechanical stress along tectonic faults. The plasma interaction model offers a complementary framework, one that accounts for the consistent statistical correlations and electromagnetic anomalies observed prior to major quakes. Regions most vulnerable to these solar-influenced seismic events are overwhelmingly subduction zones, regions where tectonic plates collide and one is thrust beneath the other. These geological settings are primed for generating the largest earthquakes on Earth. The Pacific Ring of Fire is especially at risk, comprising a vast, seismically active horseshoe-shaped belt that encircles the Pacific Ocean and hosts around 90% of the world's earthquakes. A review of magnitude 8.5 and above events since 1900 clearly reveals their concentration along these volatile boundaries. Among the most precariously positioned regions is Japan, resting atop the intersection of several major tectonic plates. The devastation wrought by the 2011 Tohoku earthquake serves as a stark reminder of this vulnerability. Farther east, the Cascadia subduction zone, stretching from northern California through Oregon and Washington to British Columbia, has remained eerily quiet for over 3 centuries. This geological silence is not reassuring. It signals a build-up of immense strain energy that must eventually be released. The Chilean coast, which experienced the most powerful earthquake ever recorded, a magnitude 9.5 in 1960, remains seismically active, pointing to ongoing tectonic stress. Likewise, the southern coast of Alaska, struck by a magnitude 9.2 earthquake in 1964, continues to show signs of accumulating strain along its tangled subduction network. What renders the current threat especially alarming is the unprecedented clarity with which these warning signs can now be tracked. Advanced monitoring systems have revolutionized the study of solar terrestrial dynamics. NASA's Solar Dynamics Observatory, SDO, captures continuous, high-resolution images of the Sun across a spectrum of wavelengths, enabling detailed observation of evolving coronal holes. Meanwhile, the ACE, Advanced Composition Explorer satellite, stationed at the L1 Lagrange point, provides real-time data on solar wind characteristics, including plasma density levels now strongly linked with seismic precursors. On Earth, a global array of ground-based magnetometers records the electromagnetic disturbances caused by solar wind interactions with the planet's magnetic field. These sensors have repeatedly picked up the distinctive patterns that tend to appear just before major earthquakes, patterns that are now manifesting once again. Additional monitoring tools, such as GPS-based ionospheric sensors, detect shifts in the vertical total electron content, another known precursor to seismic events. Specialized radio instruments also register fluctuations in the Schumann resonances, extremely low-frequency signals that often precede large-scale crustal movements. The fusion of data from multiple scientific domains marks a transformative moment in the pursuit of earthquake forecasting. Traditional seismology has long focused on past quake patterns and ground-based sensors. However, a new frontier is emerging, one that integrates space weather phenomena, electromagnetic signals, and principles of plasma physics. This multidisciplinary approach offers a richer, more intricate understanding of how earthquakes might be triggered. In light of this evolving science, practical preparedness remains as vital as ever. For individuals living in earthquake-prone areas, taking proactive measures such as securing furniture, maintaining emergency kits, and knowing evacuation routes could make a critical difference. Coastal residents, especially those vulnerable to tsunamis, should be familiar with alert systems and designated escape plans. For those following these developments closely, this moment presents an extraordinary opportunity to witness the advancement of science in real time. Several converging factors, Earth's long-overdue seismic activity, a massive coronal hole nearing Earth alignment, heightened geomagnetic turbulence, and an active solar maximum, together form a compelling test case for the solar earthquake hypothesis. Conventional geology has often treated earthquakes as exclusively mechanical events, driven by stress accumulation and release within the Earth's crust. While that model remains foundational, new perspectives from plasma physics suggest that electromagnetic influences may play a previously underappreciated role. Rather than challenging established theories, these ideas expand the framework, offering a more holistic picture of the forces shaping seismic behavior. The broader implications of this solar-terrestrial connection are significant. Should ongoing research confirm the relationship between solar activity and seismic events, it could herald a paradigm shift in early warning capabilities. Although pinpoint forecasting remains elusive, identifying windows of elevated risk based on solar patterns could provide crucial lead time, potentially preventing large-scale casualties and infrastructure losses. A particular period of concern is approaching. Beginning around April 22, 2025, Earth is expected to encounter a stream of high-speed solar wind from an unusually wide coronal hole. This feature, now in its 8th solar rotation, has grown significantly since it was first observed. Its 7th rotation coincided with a burst of global seismic activity, heightening concern as it prepares for another Earth-facing alignment. Historically, similar solar conditions, marked by sharp increases in solar wind velocity, followed by steep drops in plasma density, have preceded some of the world's most powerful earthquakes. Resources such as NOAA's Space Weather Prediction Center offer publicly accessible, real-time monitoring of solar wind and plasma density. These tools, along with ionospheric and electromagnetic field observations, may soon form the backbone of a global seismic early warning system, one not limited to tectonic signals alone, but attuned to cosmic cues as well. This unfolding synthesis of disciplines underscores a deeper truth. Science thrives not in isolation, but in connection. As the threads between solar dynamics and seismic activity grow more evident, humanity stands at the threshold of a new era in understanding Earth's most powerful forces. Sharing this knowledge could prove life-saving for those in high-risk zones, and for those eager to learn more, deeper explorations await in future content, because the story of Earth, its sun, and the invisible forces that link them is only just beginning. If you found this video insightful, don't keep it to yourself. Share it with friends and loved ones, especially those living in high-risk areas. And if you want to stay informed as new discoveries unfold, be sure to like this video, subscribe to the channel, and hit that notification bell so you never miss an update. Stay curious, stay safe, and we'll see you in the next one.